This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, the professor for this class, and this is Lecture 41, Lithography Diffraction Part 1. So we're going to have two lectures on the topic of diffraction, and this is the first part. Our reading is Chapter 7 of our textbook by Campbell. A generic projection system has these basic components. We're going to come back to some of these later, in particular how we illuminate the mask. So I won't go into a lot of details today. What I want to focus on is what happens to the light after it goes through the mask. So we have a light source and a condenser lens. First of all, the way I use the term lens is the way an optical engineer uses the term lens. The lens is a system, not a single piece of glass or a single optical component, but it represents a system designed to perform a certain task optically. And in fact, it is made up of multiple optical components. Every single piece of glass we will call a lens element. So the icon shows one piece of glass, but that's just an icon. It represents a complex system of many different lens elements. So a light source emits light. Our condenser lens grabs that light and focuses it down to a point in this objective lens over here. We're going to worry about this aspect of the illumination later, but what I want to focus on is what happens to the light when it hits the mask. So if some of this light hits the mask, it will begin to diffract. And the diffraction is the spreading out of light as it propagates away from the mask. The objective lens is there in order to grab the diffraction pattern and focus it down on the wafer. That's how we form an image. The basic idea behind imaging we'll describe in a moment, but let's begin with a phrase that I heard all the time when I first started working in the field of lithography, over 30 years ago. In those days, it was very common to describe lithographic lenses as being diffraction limited. We don't say it as much anymore because it's not really true, but nonetheless, it's useful to understand what this phrase means. Diffraction limited imaging is an imaging by a lens that is perfect. It has no aberrations. We'll talk about aberrations later, only very briefly, but we will mention what they are. But basically, aberrations are any deviation from the real behavior of a lens from the ideal behavior. So if a lens has no aberrations, that means it is behaving in an ideal way. Now that's interesting, the fact that we would call an ideal lens system a diffraction limited imaging system. What does that imply? It implies that only the effects of diffraction reduce the quality of the final image. That means even if we had a perfect lens, we would still be limited. We'd be limited by the phenomenon of diffraction. Now, diffraction limited performance is an ideal that's never completely achieved. We get very close to it with the lithographic lenses. In fact, lithographic lenses are probably the lenses that get us as close to diffraction limited performance as any lens that is made. But the real lesson that I want to impart with the use of this phrase is that even if we could build a perfect lens, that doesn't mean we could do whatever we wanted to from an optics perspective. We would still be limited by the phenomenon of diffraction. So if you want to understand what limits the capabilities of lithographic lenses and lithographic systems in general, the first thing you have to understand is diffraction. So let's go back to that basic imaging system and talk about how it works. First, we have light that's passing through the mask. As it goes through the mask, it's diffracted. We'll talk about what diffraction is in the next few slides. This diffracted light, however, we can think of as spreading out and away from the mask as it propagates. Therefore, we need a lens to capture that diffraction pattern. So the objective lens, or the focusing lens, or the imaging lens of our optical system collects that portion of the diffraction pattern that can fit through the lens and uses it to form an image. Now, here's a very, very important point that we will come back to in future lectures. the lens is not infinitely big. This objective lens has a certain finite diameter, which means it can only capture a certain portion of the diffraction pattern. And as a result, the quality of the image is limited by the portion of the diffracted pattern that we could capture. All the diffracted light that doesn't make it into that lens is lost. So we're going to study diffraction in order to understand what part of the diffraction pattern makes it through the lens and what it means when we lose diffraction information, lose part of the diffraction pattern, and what that means for the quality of the image. So let's go back to diffraction. What is diffraction after all? Well, when we hear about it in our introductory freshman physics class, it's often described, or in high school, it's often described as the bending of light as it passes through a slit or past an edge. That's not really what it is. A more correct definition is simply this is the way light propagates. If light travels from point A to point B, that propagation can be described as a propagation of diffraction. However, in many circumstances, we can think of that propagation as simply a ray that goes from point A to point B in a straight line. And we kind of ignore the phenomenon of diffraction because they're a small perturbation to the simple ray diagram approach. Light goes from A to B in a straight line. But if I look at the effects of boundary conditions, especially if these boundaries have dimensions on the order of the wavelength of light, then we see that the diffraction of light cannot simply go from point A to point B in a straight line. It involves other phenomenon that takes into account the fact that our light is a wave. So if I have light traveling, say, in the horizontal direction from the left to the right, and I put an opaque boundary with a sharp edge here, what I'll see some distance away will be a shadow. Underneath, behind the dark region, it's dark, and over here in the bright region, it's bright. What diffraction tells us is that this edge between the dark region over here and the bright region over here, so this is kind of an intensity map where it's darker to the right and brighter over here to the left-hand side of my graph. And the edge, we don't get a sharp boundary between bright and dark. Our shadows are not sharp. They're blurry, and they have some ringing phenomenon caused by the interference of light. So the phenomenon of diffraction is a little bit more complicated when you look at it in a fine detail. Now, if you were just looking at it with the naked eye, it would be hard to see all of the details of this phenomenon because it occurs over fairly narrow spaces. But if we look at it carefully, we can see this shape to the shadow, which is not at all what one might expect if you think about light as simply a ray that goes from point A to point B in a straight line. So we need a better description of how light propagates, and that's what diffraction theory will tell us. Before we get into the mathematics of how we describe the diffraction of light, I'd like to talk about this behavior heuristically using a very famous principle called Huygens Principle. Now, Christian Huygens was a famous Dutch physicist, lived about the time of Newton, and while Isaac Newton promoted the idea of light as particles, little corpuscles, particles of light. He promoted that corpuscular theory, if I finally can say it right, of light. Huygens, on the other hand, promoted the wave theory of light. It turned out they were both right in different ways, but when it comes to the phenomenon of diffraction, it's Huygens' principle that is useful for us. Huygens' principle is this. If I think of a wavefront, which is a surface of constant phase of the light, at an instant in time, I can take that wavefront and break it up into individual points of light. So consider light traveling straight down in what we call a plane wave. It's a plane wave because the surface of constant phase of the light, surface where everything on the light is identical, is a plane. So I have this plane of light and it's just propagating straight down. Think of an instant in time and take up this plane and break it up into individual points. Point, 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 point. Then allow each point to radiate light the way a point does. The way points radiate light is spherically. So radiate spherically out, and at each moment in time, the sphere has gotten larger and larger, traveling at the speed of light, and the energy of that light is spreading out over the surface area, so you get an energy going as 1 over r squared away from that point. Then, if I want to know what the wavefront is some little bit time later, I simply take the wavefront at that time, say this circle coming from this point, and here's a sphere coming from this point, and then there's another sphere coming from this point. If I added up all of these wavefronts from all of the individual points that I broke my original wavefront into, I summed them all up, I would get the new wavefront. This is Huygens Principle. Well, for the plane wave propagation, it's not particularly interesting because if I added up all of those waves, I would get a new wavefront that's just a short distance down. In fact, it'd be exactly what you thought of as a wave, a plane wave moving at the speed of light, simply moves down by that amount. So that's Huygens Principle isn't particularly useful other than the fact that it gives us what we intuit to be the right answer. But when we add a boundary, then things get more interesting. So here I've got that same plane wave of light traveling down, but now I take a mask, and this mask is opaque everywhere except for a narrow slit. So we think of the slit as coming in and out of the page as you're looking at it, or in and out of the screen as you're looking at it. So an opening in an otherwise opaque screen. Well, that means inside the screen I'll have light everywhere in the slit, but then no light underneath this ideally opaque region. Now, I'll take this wavefront inside the slit and I'll break it up into spherical waves. Let those spherical waves propagate. Now what do I see? Well, right here in the middle I see light that just keeps going straight down. But if I look out towards the edges of the slit, I see light that seems to bend around the edge. Some of this light is propagating into what otherwise would be the dark regions of the slit. This is what we call diffraction. And it's not that the light is bending because it really doesn't propagate in a straight line anyways. It's that because I block some of the light, as it propagates, some in more of a spherical radiation perspective, some of that light is now traveling in a direction that I didn't see when I had all of the rays of light continuing without being blocked. So Huygens Principle gives us a simple way of thinking about how to calculate this. But we can do even better. It gives us a way of calculating how light diffracts. Because I can write down the equation for a point source of light. The electric field has a certain amplitude and goes as 1 over r. The intensity of light, which is the magnitude of the electric field squared, goes as 1 over r squared. I can write down an equation for a spherical wave at some point in time later. Then I can add up all of the point sources within that slit. Well, if I add up point sources that are infinitely small and infinitely close together, that's called an integral. So we simply integrate over the light in the slit, sum up these waves that are coming out from each point, and that'll tell me what the light looks like some distance away. That is the diffraction pattern. When we do that, we'll find it useful to develop a very special coordinate system. And so let's do that now, because we're going to use this in just a moment. Suppose I have a mask that has some pattern on it, and the black lines here will represent the opaque regions of the photomask, and this white rectangle here is a cross-section of the glass, or the transparent region of the photomask. So I'm going to shine light on the back side. It's going to propagate through. Again, this is a cross-section. So what I've depicted here is a whole bunch of lines and spaces going in and out of the board. And then at some later point, I'm going to ask what's the intensity of light, or the amplitude of the electric field for the light in a region some distance away. And the distance away that's interesting to me is z, and whatever that distance is. It turns out that for our lens that we're going to capture the light with, our objective lens, it doesn't have a flat circular opening. It has a spherical shaped opening called the entrance pupil. So what we're interested in is what happens to the light as it enters this entrance pupil, this entrance pupil here. And so we'll ask, what are the coordinates x, and if you think of a second dimension, y coming out of the screen, what are the coordinates x and y of where a ray of light hits the entrance pupil? Right? It always travels a distance z, because this entrance pupil will be spherically shaped with its center right here at the mask. But then I'll simply ask, what is x and y coordinates of this point? When light diffracts or bends or propagates out of this mask at some angle theta, then we will define the coordinates x prime and y prime of this point using a new coordinate system called spatial frequencies, fx and fy. Fx and fy are simply the coordinates in the exit pupil, x prime and y prime, divided by the wavelength and divided by the distance away from the mask. In other words, it's just a scaled coordinate system. The reason I do this, though, is it relates this coordinate to the angle of diffraction. So you use a little bit of geometry here, and you'll see that x prime divided by lambda divided by z, well, x prime divided by z is simply sine of the angle. And if I had an angle coming out of the page and a y prime coordinate in the entrance pupil, then my angle would be sine of theta sub y. And so spatial frequencies are also just the sine of the diffracted angle normalized by dividing by the wavelength. And this coordinate system will prove to be the most useful when describing light as it enters our lens, that is, the diffracted light. Now, given that, and going back to how we would calculate what the diffraction pattern is by summing up all the point sources of light, we have then a mathematical theorem for what the diffraction pattern will look like. Skipping a whole bunch of mathematics that we don't want to deal with here, we find that the diffraction pattern can be calculated using this equation. First of all, I want to remind everyone, hopefully you remember it from some class, that light is an electromagnetic wave, and therefore it has a magnitude of the magnitude and direction of electric field and magnitude and direction of magnetic field. But knowing one allows you to determine the other in a given medium, so we only need to know one of those, and we'll spend our time thinking about the electric field of this electromagnetic radiation. So light will have an electric field. The intensity of light, which is what we see with our eyes and what our photoresist will respond to when it is exposed by light, the intensity will be the magnitude of the electric field squared. But the diffraction phenomenon is a wave phenomenon, so we're going to just deal with the electric field of the light. And the electric field of the diffraction pattern, I will give the symbol T sub m. I'll explain why I use those letters in a moment. And we find that the electric field can be expressed in these coordinates fx and fy. Those are the spatial coordinates we mentioned before, and they're just scaled coordinates in the xy plane where the diffraction pattern is being measured. Now, what does that depend on? Well, it depends on how the mask transmits light. So let me let the little m represent the mask pattern, and T sub m will be the electric field transmittance of the mask. And it varies as a function of the xy coordinates along the mask plane. The simplest mask you can think of is clear or opaque. That is, all the light's transmitted or none of it is. And we'll use that simple idea for this transmittance a lot. We'll simply say it's binary. It's either a 0 or a 1. Either all the light goes through the mask in the clear areas, or all the light remains blocked by the mask. So T sub m, the transmittance of the mask, as a function of x and y coordinates on the mask, is either a 0 or 1, and that's what this function is. Then we have this exponential minus I times 2 pi fx times x plus fy times y, and then I integrate over the whole mask. This is that summing up of all the point sources that Huygens Principle tells us about. And this is how it works out mathematically. This equation is an approximation, which is true as long as I'm a fair distance away from the mask. If I want to know what the diffracted light looks like very, very close to the mask, I have to use a more complicated expression, a more rigorous and more exact expression for how light is diffracted. But I'm not interested in that. Now I'm interested in what happens to the light a long ways away from the photomask. And in that case, we have what we call the far field diffraction pattern. That's far away from the object, so we call it the far field. This region in the far field and this equation for calculating, the transmittance, of the diffraction pattern, capital T sub m, is called Fraunhofer diffraction. And whenever we're in the far field, we're in the Fraunhofer diffraction region, after the famous German optical scientist from about 200 years ago, Joseph Fraunhofer. Now, Fraunhofer derived some of these early equations, and they were used for a long time, and then people looked at them and realized, I recognize that equation. I've seen that equation before. You know what that equation is? When I put it in terms of these spatial frequencies, fx and fy, this equation is nothing more than a Fourier transform. It's in 2 dimensions here, x and y, so the diffraction pattern, the electric field of the diffraction pattern, capital T sub m, is nothing more than the Fourier transform of the mass transmittance function, little t sub m. Now you might guess why I came up with the capital T sub m as the naming convention for my diffraction pattern. It's a Fourier transform pair with little t sub m, the mass transmittance. This is the basis of the way we often look at optical imaging systems, a method called Fourier optics, where we think about diffraction and the behavior of the lens in terms of Fourier transforms. So, if we know the transmittance of the mask, we can calculate the diffraction pattern. Really? Sure. Let's try it. Let's pick a one-dimensional feature. Our masks are really two-dimensional. Actually, they're really three-dimensional, but we'll ignore the z direction, the thickness of the absorber, and things like that. You don't have to, but it makes things a lot easier when we can just approximate the transmittance as a binary 1 or a 0. Then we'll think about a one-dimensional feature, in this case an isolated space or a slit. So we have a space of width w, and this space, I'll assume, is infinitely long in the other direction, the direction in and out of the board or in and out of the screen. Then I'll assume the opaque regions on either side of the slit also go on forever, left and right. The infinities just make the math a lot easier. So, what does our mass transmittance function look like? It's, first of all, one dimension, only a function of x, and it's very simple. It's 0 underneath the dark regions, and it goes to 1 in the clear area, and then back down to 0 underneath the dark regions. The symmetry of the situation suggests the most appropriate coordinate system. I'll let x equal 0 be the center of the slit. Okay, let's do our calculations. Now it's a one-dimensional Fourier transform instead of a two-dimensional, but the electric field of the far field diffraction pattern as a function of the spatial frequency f sub x will be the Fourier transform of the mass transmittance function. But the mass transmittance function is 0 everywhere except in the region of the slit when it becomes 1. So I can change this integral to the integral only from minus w over 2, the left edge, to plus w over 2, the right edge, because I said 0 was exactly in the center. So I'm integrating from minus w over 2 to w over 2 because everywhere else this function is 0. And in that slit region, its value is 1. So now I'm simply integrating this exponential from minus w over 2 to w over 2. Now it depends on whether you remember how to integrate an exponential. If you've forgotten, go look it up. We'll use it quite a bit in the coming weeks. So the integral of an exponential is simply the exponential back. So I get the same e to the minus I 2 pi fx x that I had before, divided by the argument in the exponential, thing that multiplies the x, the variable I'm integrating over. So I divide by minus I 2 pi fx. Then I evaluate this integral from minus w over 2 to w over 2, and I plug in those numbers. This is what I get. You might say that looks a little bit ugly. It's got i's in it. I is the complex number, the square root of minus 1. What does that mean? Where does that go? Well, it turns out it's going to disappear if we use a very important mathematical theorem called Euler's identity. You've probably seen it before, at least I hope you have. It simply says the sign of some variable x is nothing more than e to the ix minus e to the minus ix divided by 2i. That's Euler's identity. These two things are the same. And if I look here, I recognize that I've got that exact form. And I can plug it in. And when I do, I get the mass transmittance function of my slit turns into a diffraction pattern that looks like sine x over x. It's sine times pi times the spatial frequency f sub x times w, the width of the space, divided by pi times fx. This is essentially a sinc function, sine x over x function. We call it sinc function. And it's a sine wave that's modulated by a 1 over x, so that every oscillation, the further away from x equals 0, the lower the amplitude of those oscillations. Well, we'll take a quick graph if I only look on the left-hand side for a moment. Here's my mask. Here's the transmittance function. 0 underneath the dark area is 1 underneath the slit. It has a width of the slit equal to w. And my diffraction pattern looks like a sinusoid, but it's getting dimmer and dimmer. So it's high, but then it goes low, but not as far, and then it goes high, but not as far again. And it keeps oscillating around the zero axis, but gets lower and lower in its amplitude. That is the diffraction pattern, which is the Fourier transform of the mass transmittance function, equals the sine x over x function. Now, this little symbol simply means I'm taking the Fourier transform of what's inside of it. Different mass patterns will have different diffraction patterns. Next time, we're going to look at the diffraction pattern of a repeating pattern of lines and spaces. So a mask where I have the same space width w, but now I have that space next to a line of width w as well. Space, line, And my mass transmittance function, rather than being an isolated square pulse, is a pulse train or a square wave that repeats. Our diffraction pattern will be very different. And we'll look at why that is and how we get a diffraction pattern for lines and spaces for a moment. Remember what the diffraction pattern is. This is what the electric field of the light looks like a long ways away from the mask when I shine light on that mask. In other words, this is what the light looks like as it's entering the imaging lens of our optical lithography tool. Alright, that's our initial look at diffraction. We'll look at diffraction some more next time. Let's look at what we've learned so far today. You should be able to define diffraction limited imaging. What is a spatial frequency? What does this term mean? How is it used? Explain Huygens Principle. And finally, how does one calculate the Fraunhofer diffraction pattern, given that you know what the mass pattern is? That's our lecture today. We'll talk about diffraction part 2 next time. Till then.